Generating electricity this way isn't easy. If I want to run more than just a bulb, I have to put more energy into pedaling. But that's at the heart of the law of conservation of energy, isn't it? If you want more energy out of a system, then you have to put more in. Today, we'll look at 3 ways that electricity could be generated on a large scale. We'll compare 2 nuclear options, fission and fusion, to the more familiar method of burning coal. Meanwhile,
Popcorn's for us?
Sure, Christine. Help yourself. Mihai?
What does popcorn have to do with coal and uranium?
Well, it took about 200 kilojoules of electricity to make this popcorn in the microwave oven.
Okay.
So that electricity could come from a generator using 10 to 20 grams of coal.
How does that compare with uranium?
It takes 2 micrograms of pure uranium-235.
Quite a difference.
You can see it better here. 1 year's worth of electricity for a typical household, excluding heating,
Would use 3 tons of coal.
But only 140 grams of natural uranium or 0.3 grams of pure uranium-235.
Right. Now think of how many households there are in a city and then add in industry's appetite for electricity. How much coal would be required for a year's supply of electricity?
That's a big pile of coal.
Now try to imagine how much coal we'd need over the next 40 years.
That's not a pile, that's a mountain.
But you wouldn't need nearly as much uranium.
Why is that?
To answer, we'll have to look at how we get energy out of uranium.
Okay.
Once we've done that, we can think about how we might produce our electricity 40 years from now.
Sounds good.
when coal is burned, electrons are rearranged as the chemical bonds are broken. The forces involved in these bonds lead to energies that are less than 10 electron volts for most atoms and molecules. On the other hand, nuclear reactions involve rearrangements of nucleons that are held together by the strong nuclear force. This force is much greater than the forces involved in chemical bonding. So the energies released when nucleons are rearranged are also much greater, millions of electron volts. That's why burning 1 gram of coal releases 29 kilojoules of energy, while a nuclear reaction involving 1 gram of uranium-235 releases about 96.4 million kilojoules of energy.
Here's another way to think about why the energies from nuclear reactions are so large.
Looks familiar.
Made Albert Einstein famous.
Now, according to Einstein, mass can be converted into energy.
So this is the mass that's converted.
And that's the energy you get.
So what does the c squared stand for?
It's the speed of light, squared. Now, this constant is really big. So if you put in even the smallest mass,
You get a huge amount of energy.
right, so we can expect to see a change in mass going along with the energy change for nuclear reactions.
If you took an alpha particle and compared its mass to the mass of its parts, you'd find that they're not the same. The values shown are all in units of 10 to the negative 27 kilograms. The complete particle has less mass than its individual parts. This difference in mass is called the mass defect. The mass defect in this case is the mass of the parts, 6.69692, subtract 6.64646, giving 0.05046 times 10 to the minus 27 kilograms. Einstein's mass energy equivalence predicts that the mass defect can be accounted for by a change in energy. The mass defect, 0.05046 times 10 to the negative 27 kilograms, is multiplied by the square of the speed of light, 3.00 times 10 to the 8th meters per second, to give an energy equivalent of 4.54 times 10 to the negative 12 joules. multiplying by 1 electron volt over 1.60 times 10 to the negative 19 joules gives an equivalent energy of 28.4 mega electron volts. Einstein's equation effectively means that the laws of conservation of energy and conservation of mass must be combined.
So Einstein's equation means mass and energy together are conserved in this reaction.
But what does it mean to have this energy term over here?
Well, this is the binding energy. It's the energy you'd have to add to the alpha particle to break it up into its parts.
So the alpha particle doesn't have this energy?
No, it doesn't. If it did, it would break up into 2 protons and 2 neutrons.
What if the reaction went the other way?
Well, it says you'd end up with an alpha particle and lots of energy.
This type of reaction is called fusion. It's a stellar source of energy.
Fusion is the energy source that fuels the stars. The energy from fusion lets us see galaxies, even though they're hundreds and thousands of light years away. Fusion is the energy source of our own star, the Sun. Without fusion, there'd be no light and no life on Earth.
The fusion reaction in the Sun involves 4 hydrogen nuclei being fused into 1 helium nucleus. The reaction also produces 2 positrons and involves more steps than what is shown here, but the main idea is that lots of energy is released. 26.7 mega electron volts. Since the hydrogen nuclei are positive, they all repel each other due to the Coulomb force. The strong nuclear force overcomes this repulsion and fuses them into a helium nucleus if they can get close enough. Remember, the strong nuclear force is a short-range force. To get them close together means that they have to have lots of kinetic energy to overcome the Coulomb repulsion.
In the Sun and other stars, this condition occurs naturally. Inside, very high temperatures, millions of degrees, and equally high pressures ensure that the particles will come close enough and with enough energy to fuse. The energy released from each fusion reaction helps keep the temperatures high, so the reaction is self-sustaining.
To some, fusion is the ideal energy source for the future.
Why is that?
Think of the reaction. What are the reactants and products?
Well, the fuel's hydrogen.
And the world's oceans are full of hydrogen. It's CH and H2O.
And the product's helium.
So there's no hazardous waste. Helium is an unreactive, harmless gas.
And you get lots of energy.
Right. Fusion reactions in the lab give about 28.4 mega electron volts per helium atom. That works out to about 6.84 times 10 to the 11 joules per gram of helium produced.
Hey, that's more than uranium.
There's just one hitch. What kind of container can hold the insides of a star?
Right. Fusion needs a startup temperature of millions of degrees.
See what you can find out.
The conditions that can support fusion are described as thermonuclear. A thermonuclear weapon, commonly known as a hydrogen bomb, represents an uncontrolled fusion reaction. Nuclear weapons testing has left traces of radioactive elements in the atmosphere. For fusion to be used for the peaceful purpose of generating electricity, the reaction must be controlled, releasing the energy slowly.
The major challenge in making fusion a source of energy is finding something to hold the reaction. 2 ways of confining the reaction are now under development.
The first approach is magnetic confinement. The fusion reactants are a plasma consisting of positive ions and electrons, so they can be manipulated by electric and magnetic fields. The magnetic fields hold the plasma like it was in a magnetic bottle. This tokamak reactor design uses magnetic confinement.
The other approach is inertial confinement. In this scheme, The fuel, a pellet of hydrogen, is dropped into a reaction chamber and is then subjected to an intense energy beam supplied by lasers, electron beams, or ion beams. The idea is if these beams can strike the pellet at the same instant, then perhaps the inertia of the pellet will hold it together long enough for it to implode. The implosion would create the high temperatures and pressures necessary for fusion. The NOVA Laser facility in California is exploring the potential for inertial confinement.
Keeping the plasma where you want it is a challenge, but the rest of a fusion reactor is very similar to any generator.
The fusion reactor just uses a different way to heat water to steam for the generators.
Right.
But fusion reactors are still experimental.
What about the nuclear reactors used today?
Yeah, how do they work?
You'll find fission reactions throughout the history of 20th century physics. The first type of nuclear reaction studied was natural radioactivity, in which one nucleus spontaneously changes into the nucleus of another atom, with the release of alpha or beta radiation. Although scientists understood that this process involves tremendous amounts of energy, they also knew that this reaction occurs over a very long time for any collection of radioisotopes.
The name CANDU reactor is short for Canadian deuterium-uranium reactor. Deuterium is an isotope of hydrogen that's used in the heavy water of the reactor. Uranium, in the form of uranium oxide pellets, is used as fuel.
From earliest studies of radioactivity, scientists knew that one nucleus could naturally decay into the nucleus of another element with the emission of a particle. Scientists wondered about the reverse process. Could one nucleus absorb a particle to create the nucleus of another element? To test this idea, they bombarded uranium, the heaviest element known at that time, with neutrons. They hoped that a new nucleus would form, marking the discovery of a new element. Working in this area, Otto Hahn observed something quite unexpected. Sometimes the uranium nucleus split apart into two fragments. Lise Meitner worked out a theory of this reaction. Meitner called the process fission because of the similarity with the division of living cells. In her paper, which was the first research published on the physics of fission, she predicted the emission of more neutrons and the release of energy. Here's one example of a fission reaction. Let's see if Lise Meitner's predictions hold.
So a neutron collides with a uranium-235 nucleus,
Splitting it into isotopes of barium and krypton.
plus 3 more neutrons, and releasing energy.
And that's what Meitner predicted.
Exactly.
Although uranium is found in soil all over Earth, the concentration is rarely high enough to make it economical to mine. Once ore is pulled from the ground, it's crushed to the size of sand during milling. Residues or tailings from this process must be carefully managed, since they contain radioactive daughter products of the uranium decay series, such as radium and radon gas.
Here are two more ways that uranium-235 can be fissioned into smaller nuclei.
Each one starts with a neutron being added to the uranium.
Good observation. Since each reaction depends on a neutron to start it off, they're called induced reactions.
And each one ends with energy and neutrons being emitted.
Right. These neutrons are essential for a chain reaction.
Chain reaction.
Well, if the reaction is to sustain itself, neutrons must leave to induce more fissions.
So one reaction can cause another one.
Right. That's a chain reaction.
At a refinery, Uranium concentrate from the mine is processed to form hard ceramic pellets. These are fuel for the reaction. The pellets are packed into rods, which are arranged in a fuel bundle. The bundles are then organized into a special pressure tube. It takes 390 pressure tubes, arranged in the reactor vessel called a calandria, to make the core of a CANDU reactor. The calandria is positioned on its side so that refueling can occur without the whole reactor being shut down.
Does Einstein's equation explain the production of energy in a fission reaction too?
It does. About 173 megaelectron volts of energy per uranium-235 atom are liberated by the reaction.
So with the conservation of mass and energy, more energy here means more mass on the other side.
Right. Now can you tell me how much mass was converted to energy?
Einstein's equation will come in handy here.
Most of the energy released through fission is in the form of kinetic energy of the products. The kinetic energy of fission products and neutrons causes the temperature of the fuel and the heavy water surrounding the fuel to increase. Since each collision of a neutron with the heavy water has the effect of moderating or reducing the speed of the neutrons, the heavy water is said to be a moderator, as well as a part of the heat transfer process.
We got an answer.
Super. Take me through your solution.
Okay, first we converted the energy units by multiplying by 1.60 times 10 to the minus 19 joules per electron volt,
giving us an energy of 2.77 times 10 to the negative 11th joules.
Looks good so far.
From there, we just rearranged Einstein's formula.
So mass is equal to the energy of 2.77 times 10 to the minus 11 joules divided by the square of the speed of light, 3.00 times 10 to the 8th meters per second.
Giving us 3.08 times 10 to the negative 28th kilograms.
Well done. Even though this mass is less than 1% the mass of the uranium atom, you still get lots of energy.
After a bundle has been in the reactor for about a year and a half, the proportion of uranium-235 has dropped to the point where the fuel bundle has to be replaced. The spent fuel is placed in a deep water tank, while all the fission products with half-lives less than a year decay. After 1 year, the spent fuel is only 1% as radioactive as it was when it first came out of the reactor. For the first 5 years, the bundles continue to put out heat, so they're kept in water tanks. After 5 years, they're transferred to concrete storage canisters. And after about 50 to 100 years in dry storage, plans call for the spent fuel to be sealed deep into stable rock formations, such as the Canadian Shield.
So heat generated by the reaction products is transferred to the heavy water.
Right. The heavy water transfers the heat to ordinary water in the steam generator.
The heavy water stays in the reactor building the whole time and doesn't mix with the water that's used to make the steam.
So once the steam has been produced, what happens?
The steam is used to turn the turbines, which generate the electricity.
Just like in any generator.
Most of the electricity generated is transformed, then transferred to the power grid.
But some is kept behind to meet the demands of the whole complex.
I see.
The use of heavy water as a moderator is an extra safety feature of the CANDU design. The fission reaction can only continue if there is a supply of slow neutrons. Without the moderator, the neutrons move too fast to sustain fission. So if the reactor becomes too hot, dumping the heavy water automatically stops the reactor.
So we've come full circle.
Yeah. How will we be generating electricity 40 years from now?
Well, we've looked at coal, fusion, and fission. Which is the best choice?
Why don't we each take one of them and present a summary in terms of positives and negatives?
I'll take fusion.
Okay, I'll look after fission.
So that leaves coal for me.
Each year, About 12 million kilograms of uranium are mined in Canada, with less than 15% used domestically. Even though Canada has about 20% of the world's uranium, the supply will be gone in less than 20 years if no other deposits are found.
So what are the positives of fusion?
Well, there's lots of fuel because there's so much water here on Earth.
Every water molecule has hydrogen.
Yeah, it's hard to imagine that we'd ever run out.
Sounds good. Anything else?
What I like best is that fusion is environmentally friendly.
Right. No hazardous waste or emissions like CO2 that contribute to global warming.
And now for the downside.
It's still on the drawing board. The research reactors use up more energy than they produce.
It isn't easy to create a bit of a star here on Earth.
That's why these reactors will be really expensive to build.
Very likely.
There's a lot of years of research ahead before this is a reality. High temperature technology is really difficult to build safely.
Well done. Go ahead, Mihai.
One positive for fission is that there are no fossil fuel type emissions like CO2.
So it doesn't contribute to global warming.
Right, and there are no nitrogen or sulfur oxides.
So it's not causing acid rain either.
And in terms of the negatives?
Well, the disposal of waste is a problem. Spent fuel rods are highly radioactive, and there is no known way to recycle them.
So the wastes have to be stored.
Exactly. Another problem is what to do with the reactor itself.
What's the problem there?
Well, it has a limited lifespan. The neutrons that sustain the fission reaction can penetrate the structural materials of the reactor.
So when these reactors are decommissioned, what will be done with the tons of radioactive steel and concrete?
Yeah, the environmental impact of fission reactors is a complex question.
And there is a very small chance of a catastrophic accident.
There are no pat answers to this one.
Over to you, Heather.
The first thing in favor of coal is that it's an up-and-running technology.
Coal's been used for a long time.
It's also a relatively inexpensive form of energy, and there's lots of coal.
And now for the negatives.
The big problem is the disposal of hazardous waste.
Sounds like fission.
Well, with fission, the wastes are concentrated in small volumes, so they can be stored at the reactor site.
Coal requires tons of fuel instead of the grams used in fission.
So there must be tons of waste instead of grams.
And most of them go up the smokestack or are dumped into the environment.
Which leads to acid rain, smog.
Not to mention the possibility of global warming.
The impact of these wastes on the environment is significant, and mining accidents will happen.
Coal contains small quantities of uranium, thorium, and other decay products such as radon. But the volume of coal burned is large. For every kilowatt hour of energy produced, coal burning stations release more radioactive materials into the general environment than do nuclear reactors.
We may be smart enough to solve our problems with technology, but we are not smart enough to foresee the problems that our technology will create.
You're quoting
Albert Einstein.
So what does that say about how we generate electricity?
maybe fusion won't be a perfect energy source after all. Maybe it'll have its dark side.
So does that mean we stop developing fusion as an alternative?
I don't think so. Compared to coal or fission, it still looks good.
And there are other alternatives.
Yeah, I think we can start with energy conservation.
Right. That's a step towards preserving the environment.
Good work.
The bike has a big advantage when it comes to generating electricity. If I start to plug in too many things, I get immediate feedback, exhaustion. Unfortunately, the feedback that the environment gives us isn't always immediate, and the collective effects of millions of people using more and more electricity is enormous. Applying the principles of energy conservation is essential if we are to look after our world in motion.